Good afternoon, all of you. Welcome to 360 interview preparation session. So we'll discuss on dummy variables and what is the importance and how we can able to create dummy variables. So what are dummy variables? And why we have to create them. So when your data contains categorical variables, we're going to create a dummy variables. Like our data contains categorical variables. So in categorical variables, there are different types. We can say nominal type and ordinal type. So based upon the category, we're going to create different types of dummy variables. And why we have to create dummy variables? For example, I'm considering a data set. So empty cars, I'm considering, where I have a different vehicles with a different fuels, and I have other variables which are numerical. Let's say speed, weight, volume, and I'm having miles per gallon. And here I'm having fuel type, say car type and fuel type. So I'm having petrol, diesel, and CNG. So I want to use this information in my analysis as well. So I can't use this information directly. So what I have to do is I have to convert this nominal data. This is names, so we can call it as a nominal data into dummy variables. So after converting into dummy variables, I can use this data in my analysis. So how I can able to convert this categorical variables into dummy variables? How to convert dummy variables? So there are different strategies. So first one we discuss is, say, label encoding, where your data is a categorical data is nominal format. Then you can use label encoding. For example, here petrol, diesel, and CNG. So I'm going to create dummy variable for petrol. If in my data I see petrol, then I'm going to assign 100. If diesel is up here, then it is 010. For CNG, 001. So in this way, we're going to create dummy variables. Whenever you're creating dummy variables by using label encoding, what problems you'll get? So the question is, what are the drawbacks? With label encoding in dummy variable creation. So first drawback is you can able to fall into dummy variable trap. So dummy variable trap means you're going to consider all dummy variables in your analysis, then your model will perform overfitting problems. It leads to overfitting problem. Next, if I'm having, let's say, 100 variables, 100 categorical variables like petrol, diesel, like other sections I have. So I have to create 100 dummy variables. Then I'm going to face the curse of dimensionality. One is dummy variable trap, another one is curse of dimensionality. We have seen the dummy variable means you're going to load all these things, then you're going to having overfitting. It leads to overfitting. And what about curse of dimensionality? Let's say I'm having 100 categorical variables and I created 100 dummy variables. And I'm going to create 100 columns here. Means my data set of, let's say, 1000 into 20. This is my data set shape size, you may call it as 100 rows and 20 columns are there. After converting into dummy variables, the categorical variables, then what it will become, let's say there are 100 categorical variables, then it will become 120 . So my dimensions of the data set is going to be increases drastically. These are the problems whenever you're going to convert into using label encoding. So how are you going to come out of it? The question is how to avoid falling into dummy variable trap. If your categorical variables, this nominal data is a limited one, let's say, then it's okay and we can create. But avoiding dummy variables, there is a strategy called dummy coding schema. Dummy variable coding schema or dummy schema you can call. So in this schema, we're going to take D-1 strategy. In label encoding, let's say you're having K categorical variable, it's going to be create K dummy variables. So in dummy coding schema, if you're having K categorical variables, it's going to create K-1 categorical variables. Then how it will work, the schema. So let's take the same example here. So whenever petrol is appear in my data, I can take 100. Whenever diesel 010. Then in two places, here I didn't see any one, here also I didn't see any one for third observation. Then what it could be? It could be CNG, right? Then I don't want this one. If it is true, then it is petrol. If it is true, it is diesel. If either of the not true, then this is going to be CNG. So I don't need this dummy variable in my analysis. So in this way, we can able to reduce, dummy variables to D-1. So then you can get out of this problem, overfitting. overcome with D minus 1 strategy. Okay, and coming to curse of dimensionality, how we can able to treat this one. Let's say I'm having 100 variables, categorical variables. I created 100 dummy variables. Then in these variables, I can see most active or as most frequently repeated value. Most frequently repeated variables. I'm going to catch these most frequently repeated variables. Instead of 100, 10 variables only repeating every time. Then I'm going to consider those 10 variables only instead of 100. With this strategy, I can get over this one, curse of dimensionality. Then how you treat ordinal categorical variables, ordinal variables in dummy variable, in creation of dummy variables. So when your data is in ordinal, or your variables in ordinal form, we're going to use one hot encode. So how it's going to be created in ordinal form? Let's say I'm having country's name alphabetically. Let's say countries alphabetical form. It follows the order A to Z. Right. So I can create the country which is starting with alphabet A. Then I'm going to give 0, B equals to 1. Okay. So like that, I'm going to levels. You may call it C equal to 2. I'm going to design these levels and I'm going to convert this into dummy variables. So in case of, let's say, a class, we're going to have CR, class representative, course CR, maybe class leader will be there. I'm going to convert them. They follows one order, right? Let's say it's being 1, 2, 3. So I'm going to convert this ordinal data into dummy variables. I'm going to convert into numerical 1, 2, 3. Then what if you're going to have n ordinal data? Then you're going to convert into n categorical, n dummy variables again. But an ordinal data is going to follow some order. It's not going to be too lengthy. Most of the cases. For example, if you're going to consider a police department and their ranks, say DG, okay, SP, DSP, SP, okay, and SI, CI. You're going to give ranks to them, levels 1, 2, 3, 4. So whenever your data is in ordinal shape and you want to convert into dummy variables, then you have to use one hot encoding. So one is one-hot encoding, label encoding, dummy variable schema, and effective coding schema that I told you that there are 100 categorical variables and only 10 are performing very well. We're going to consider that. That will come in effective coding schema. And bin counting schema. So if categorical variables having related to each other, I'm going to create a bins or else buckets, you may call the bin 1, bin 2, and bin 3. Instead of creating individual dummy variables, I'm going to push similar categorical variables into one bin. Then I'm going to create dummy variable for this bin. Okay. This is where here we can use effective coding schema. Bin coding schema. Feature hashing is also similar one. We're going to create the frequency list similar to that one, and we're going to use those dummy variables. So in dummy variables, what are the problems we'll get? One is dummy variable trap, dummy variable trap. Second one is curse of dimensionality. What problems will get? Overfitting. Here also overfitting will get more dimensions. Are you going to come out of this one? D-1 strategy. Here we're going to consider most frequently occurring variables. So whenever you are dealing with data, how to handle let's say scale of data or dimensions of the data. So example, my data contains values. First column ID 1, 2, 3, 4, 5. And here I'm having 10, 20, 30, 60, 40. And here I'm having 0 0.1, 0 0.5, 0 0.6, 0 0.7, let's say 1. And here I'm having 200, 300, 250, 450, 550. And here I'm having 1 lakh, 2 lakh, 4 lakhs, 8 lakhs, and 7 lakhs. So whenever you look at each and every column or every field, the scale is not same. This is in one scale, this is in one scale, this is in one scale, this is in one scale. So whenever you're going to find out the variance or standard deviation from its mean value, and you're going to compare with the other feature, other column in the data, it seems to be more dispersed than the other variable. Let's say if I'm going to consider the first column, that data is look like this. The last column, that data seems to be, spread in such a way. So what we have to do is we have to normalize this data. We have to scale. So a lot of sparsity will be there. So what I want to do is I want to normalize this data. It means I want to bring all these values under one scale. Bring data into data and under one scale. So doing such, this is called applying normalization or standardization. So when I'm going to normalize this data, then all these values going to be converted into same scale. Let's say these values and all these values going to be converted to one scale. It seems to be like ID. You can, no need to convert ID. Let's keep aside and look at all values. It's going to convert 0.12, 0.1, 0.01, 0.2, and it is 0.01, 0.5, 0.26, so on. The last column as well, it's going to be converted to 0.1, 0.2, 0.4, 0.8, 0.7, so on. All the data is going to be converted into it, come under one scale. It follows one scale. Then when you're going to look at the variance and standard deviations, you can see less sparsity from column to column. So how we can do this normalization? How to perform normalization or standardization? So there are methods to convert this data into one scale. So one is same normalization or standardization, we call it, and min-max scaling, and robust scaling. So before you're going to apply these methods, you have to check your data, that your data is having any outliers. Check for outliers before going for scaling. What is outlier? Outlier is an extremely high or low value in data. Again, what is the problem with these outliers? Extremely high values and low values. Of course, these are valid points, not mistyped or typos, typo errors. Valid data only, let's say. Then what is the problem with these outliers? Yes, Sumesh, extreme value, of course. My question is, what is the problem with outliers? Of course, it's extreme value and it is a valid data point. It's actual data only. What is the problem with it? So the problem with the outlier arises. Problem arises. Yes, it will change average value. Okay. Problem arises when you're going to consider mean or average to impute missing values, to treat missing values. It will influence the output, of course. When I'm treating these missing values with data which is having outliers, I'm taking mean. Whenever we're going to treat missing values, we'll take mean, median, mode, variance, standard deviation, right? If I'm going to consider mean as my measure to replace, then these outliers going to influence me. Okay, so I don't want to use mean. I'm going to use another parameter. Okay. So you have to check here whether your data is going to have outliers or not. If outliers are there, before you're going to do normalization, try to treat them, try to modify them or remove them. What will happen? Because if you're going to apply normalization, outlier also going to be normalized. Later you fail to identify this one. So identify outliers are there or not. Then apply. And normalization and standardization, min-max scaling. Okay. These will convert those outliers in scaling. And coming to robust scaling, where we're going to use quartiles like IQR, we're going to take as a measure interquartile range. And it will not affect by outliers and robust scaling method. So here we're going to consider x minus x mu by, I think, IQR. I forgot the formula, but it seems to be like this. So in normalization and standardization, we're going to use x minus mu by sigma. X is our data point, mu is mean. So we're going to apply x minus mu by sigma to standardize the values. And min-max scaling, it is x minus x minimum by range. So with this, we can scale the data. standardization, min max scaling, robust scaling, it's x minus median of x by IQR. Sorry, this is the equation, is x minus median of x and IQR of x. So look at the equation. Okay, it is taking median. It's not taking mean. So it is not influenced by outliers. So this scaling, robust scaling, not influenced by outliers. So if you think your data is containing any outliers, you can use this method to normalize your data. So coming to transformations, why we have to transform our data, why we have to apply transformations on data. So we have different transformation, log transformation, exponential, square root, reciprocal, box. Yes, there are different methods. Yeah. So my question is why we have to apply transformations. So whenever you're going to apply these transformations of onto the data, the shape of the data is going to be changed. For example, before applying, let's say, log transformation, my data is going to be look like this. So I can fit a linear regression line through it. And my data is, having like this somewhere. I'm unable to, make a predictions or inferences about it if data is away from its centrality, and maybe I'm unable to fit a regression line. So I can apply a transformation onto this data. Let's say I'm applying log transformation. Then my data is going to be change its shape to this way. Maybe previously it's slightly linear. Now it's going to be changed to curvy linear. Now I'm going to use another machine learning algorithm to fit or follow that shape. Then my regressor going to be follows in such a way. So after changing the shape means applying transformations will try to change the shape of the data. And we can able to fit our regressor better fitting of regression curvilinear here if I'm going to use polynomial regression. If you're unable to achieve the proper fit and actual data, we're going to apply the transformation to change the shape of the data. So for example, I'm going to consider simple linear regression equation. Let's say y equals to beta naught plus beta 1x. So I'm going to apply log transformation. Beta 1 log x. Then my shape is going to be changed. Yes, here if I'm going to change the shape, what about the inferences of data? So when data is in its original format, I can draw inferences. Then if I changed by applying transformation, I changed the shape, then how I can able to draw inferences of this data again. So there is a reduced power going to be reduced while drawing inferences. When you're going to use these transformations, you're going to lose power of drawing inferences about the data. But to achieve the results, sometimes we have to apply these transformations onto the data. So log transformation, exponential, for example, if I'm going to take log y and beta naught plus beta 1x. If I'm going to take log to my independent variable, it is okay, I can able to draw inferences. If I'm going to take log y to my output, so explanation going to be lost. So I'm going to cancel out this one, then what will happen? Y equals to e power beta naught beta 1 x exponential. Square root, maybe here I'm going to take square root to it. Maybe x equals to 1 by x I can take for reciprocal. And Box-Cox method and JSNIS, they are having different strategies to follow. So by applying these transformations, I can achieve what I want to achieve. I try trial and error. There is no particular rule which one you want to use. It's like trial and error, you can use this. So in data cleansing and data preparation, we follow all these steps. So one is typecasting. It is like converting types or as classes, maybe int to character to int to double. What we're doing is we're changing its type. It's called typecasting. Why we have to use typecasting? And when we have to use. Let's say my data contains date and let's say months in names, let's say, and I'm having temperature, other parameters on it. Date, which is in numerical format in my data, let's say 1/1/21, 3/2/2021, like that. And months names I have maybe January, February. Timings, sorry, temperature is 25 degrees, and I say 30 degrees. So time and data, based upon the data set, time is going to be changed. Format. Some people, they're going to use, let's say, first they're going to use month, next date, day, and year. In some data sets going to have first day will be there, next month will be there, year. In other cases, you're going to have year, month, and date. These formats. Anyhow, if I don't want to use this data, I just want to treat as a string. So I'm going to convert this data into character. Maybe it is in format of date. I'm going to convert into character. So how I can convert? As dot character. I'm going to provide this date here. Then it's going to be convert into character. So it will give you quotes. It's going to be embed this in quotes. If you're going to see this data, it look like this one. It means it converted into character. Month is already a character. Now here it is, let's say 25, 30 degrees is in integer form. So when I'm running my analysis, after doing analysis, I'm getting error that the type of data file is integer, not float. It shows error. If it is float, I'll run the entire analysis and you'll get the results. But it throws at me error that it's saying it is in integer. I want floating values. Then I'm going to convert this into floating point. So how I can as dot float. As dot float, I'm going to give this temperature column here. So it's going to be convert to float. So it seems to be 25.0, 30.0 degrees centigrade, degree centigrade. So in this way, we're going to convert the types. It's like example int to big int, in some cases into double, numerical value, or else float to integer, integer to character. So using a typecasting, data cleansing and data pre-processing is one method to look into the data classes or types, you may call it as. Then as per requirements, we're going to change this one. Then we're going to look for, is there any duplicate values are. How are you going to handle duplicate values? Duplicates. Or another question you may get, that how duplicate data will be created. Data created. So duplicate values will create. So if whenever you're going to record the data, for example, I'm collecting data by using survey. So I took survey from same person in different time periods, let's say. Day one, I did survey in one place and I recorded all the data. And day two, the same surveying, I accidentally or unfortunately, I came across the same person. So in this way, again, I'm going to collect the data. And I'm going to give this to one person to create a table out of it. Then he didn't know. He simply enter whatever data I have given here. So in this way, duplicate values can be created. So there are other examples how duplicate data created. You can look and do a research. So how we can able to handle this duplicate data? So you have to identify how many duplicates are there and how many unique values are there. So in R, there is a function duplicate. Let's say is duplicates. Then I'm going to provide my data set here. Then it will show you how many duplicates are there. It will give you a number, how many duplicates. Then I can search for unique values. And it will show unique data set. It will show how many unique values are there. Then I'm going to write a function here. If this is not duplicate function, and I'm going to append the data, into my data, another data set I'm going to create. So which are unique values, that is going to be append into my data. Then I can able to avoid this duplicate values. So it is like removing duplicates. So that's all for today, and thank you all of you. Thank you for attending.